I'm excited to have Sebastian Benthall talk to us about computational economics. So take it away.
Thanks a lot. Excited to give this talk. This is a surprise talk opportunity, so it's a little bit less about code than you might expect for talk, but hopefully still interesting. Also, computational economics, very interesting field. I'm not an economist, and so this is an opinionated take by a non-economist about this field. I do work on Econ-ARK, which is an open source library for computational macroeconomics. So let's see how this goes. First, I want to talk briefly about open source and its role in economics, especially macroeconomics, and then recent research in deep learning in economics methods, and what this means for reproducibility in economics moving forward. Many economists have heard of DINAR, which is an old project that began in 1994. It's about dynamic stochastic general equilibrium modeling. This is used to model whole national economies by like central banks, and it's based on a rather old paradigm of economic modeling called representative agent modeling, where you take like an entire sector of the economy, like all consumer households, and you model it as a single representative agent. And then you look at the equations as this representative agent optimizes for its consumption over time, and it participates in an economic production function. And this has been sort of the mainstay of economic modeling for decades. This is a preprocessor written in C++, it's a domain-specific language. This has been the height of open source computational economics. But when the great financial crisis of 2008 happened, among other things, this representative agent modeling kind of paradigm came under a lot of critiques because there's sort of there's a fallacy of ecological fallacy, and a fallacy of decomposition. Like you can't model many heterogeneous agents as just a single agent. It doesn't really make sense. So people started thinking about how do you model an economy where you have many diverse agents interacting, getting elements of agent-based modeling that started to percolate in. There's questions about, can you relax really strict assumptions about perfect rationality in these models, have more bounded rational models? Incomplete versus complete markets, that has to do with how much risk in markets can be sort of hedged out in sort of various kinds of insurance contracts. What do you allow for? So a lot of these sort of simplifying assumptions have been relaxing because we need more realism, and also there's new ways of developing software and doing computation. So we've got faster Python, a lot of economics is being done in Julia now, there's GPU programming, open source development workflows have evolved a lot, there's new computational science tools, that's why we're here. Right. So heterogeneous agent modeling has been becoming more and more common and accepted by a field that's notoriously slow to adjust to new ideas. The problem is that the more complex you make these models, the more computationally complex it is to solve them. Right? And because in economics, frequently the agents are actually solving optimization problems, which are the problems implied by the model they are in, there really is this sort of trade-off between like modeling expressivity and computational complexity. Right? But nevertheless, people are building models where you have agent microstructure of heterogeneous agents as dynamic optimization problems, and then aggregating those individual agent behaviors with a market mechanism. And this is kind of an abstract version of what these dynamic optimization problems look like. You might have some exogenous state process that gets like, maybe some exogenous noise every time period. It adjusts, you can think of this like a Markov process running in the background, and then an endogenous state process that's dependent on individual actions. So, if someone takes an action X out of some possible set of actions, capital X, driving this endogenous state forward process, ratchet, and people try to optimize something. In this case, a kind of lifetime reward function. So, someone earns R, little r in reward every period. They discount future reward by this beta, and so they sort of expect how much, given a particular kind of consumption strategy or something, will they accrue over time. This is looks very similar to a Markov decision process. This is all sort of backed up by earlier control theory. And this is what gets adapted to computational economics and has been for some time. So here's one example problem, which might sort of give the flavor of it. So here, W is how much wealth the agent has at any time period. They consume out of that wealth, W minus C, and then what they have left over, they get a rate of return on that R, and they earn some income stochastically. So they get, this is like a log normal transitory income shock, is the way they call it. Basically, you earn a certain amount of money at random every period, and the question is, how much do you consume? You can either consume to get utility today, or you can save to consume that later, getting the rate of return on it. So the way people have typically solved these kinds of problems, and there's many, many methods, more than I can go over here, but this is kind of the backbone, is some kind of grid-based dynamic programming solution. So that lifetime reward function implies this recursive Bellman equation. It's recursive because there's a V on both sides, right? And so the value of the period, value of having a certain amount of money in the next period is then discounted, and then you add how much you get as a reward for consuming today. And then you can solve for this value function and read off of that the best possible policy action of how much to consume each period, for example. There's a lot of different ways to solve problems like this. Reinforcement learning has not been very common in economics, but it's becoming more common now. Sort of AI is getting into the economics profession. And in a finite horizon problem, you can use backwards induction, which is very similar to this. But this is sort of the most basic dynamic programming algorithm used here. It would be you set an arbitrary value function, and then you simply compute forward with an optimization problem on each place in the state grid. You find the optimal action to take at that step based on this equation, and then you just back up that value that's now computed, adjusted, and you wait for convergence. You repeat that cycle until you converge. And there's two sources of kind of computational complexity here. One, since often we're talking about continuous values, like amount of dollars, right? These continuous spaces have to be discretized first. So we're looping at step 2 over every grid in a discrete state space, every grid point in a discrete state space. And so, you might discretize that to 5 points or 10,000. And the more points you add, the more complex this step 2 is going to be. The other problem is if you have a high dimensional state space, then of course your grid size is increasing exponentially. And this has put a lot of pressure on these economics researchers to have very simplified models, which means that there isn't as much realism as you might expect here. This is the curse of dimensionality. It goes way back to Bellman and control theory, et cetera. So there are a few different open source library packages developed by different economics labs that are based around this paradigm of dynamic programming solutions to these problems. I'm going to talk about just a couple that are kind of our favorite on our team. So Dolo has a very interesting YAML-based configuration language for its models that compiles to both Python and Julia. It has some support for GPU and NumPy optimizations. When it simulates a model forward, it uses something called transition matrices, which means it maps explicitly how likely it is any particular state is going to go to a different state, rather than doing a Monte Carlo simulation, which I'll get to it a bit. But this particular library has some limits to what kinds of models it can represent, as you might expect. So economists are often interested in aging and mortality of agents. They're often interested in market aggregation. That's not built into Dolo as it currently exists. And then there's HARK, which is part of the Econ-ARK project, which is a NumFocus sponsored project in this area. HARK is in Python only, but it's more tailored to these sort of life cycle problems of aging and mortality. It uses Monte Carlo simulation, and it does market aggregation. But one thing that it does is it hard codes a lot of the details of each model, which is quite common across the field. It's hard to find sort of this sort of domain-specific language approach to modeling, though it was very successful in Dynair. Right? And it's partly because of the computational constraints that people have been hard coding these models in order to sort of eke out performance as they try to test out new theories. Right? And this is bad for reproducibility in the field. Right? Something that's been changing in the last 3-4 years is computational economics has discovered deep learning. And these are just some of the many papers in this area. And I'm going to talk about one particular paper that I really like as kind of a representative of the flavor of the contribution. So the idea is you construct a loss function based on the model equations such that if you minimize that loss function, you wind up solving essentially everything about the model, including the parameterization of the decision rule. And that loss function can then be used in a neural network. And the intuition for why this is useful is that rather than doing the dynamic programming solution of trying to solve for every point on an n-dimensional grid, the idea is you first sample points from the distribution implied by the state of the model, right? And then you compute the empirical loss on each of those points, and then you update based on, you like basically backprop the gradient on those particular points. And the intuition here is like if you think of like a hypersphere inside a hypercube, the hypersphere's volume is going to be much smaller than the hypercube. And another way to pump this intuition is a probability distribution has only a probability mass of 1, no matter how many dimensions it is. So if you're sampling some finite number of points from an n-dimensional distribution, it's only going to get from points from where there's a high probability mass, and that's not most of the grid, right? So what happens is if you repeat this process several times, is your sample winds up converging on the ergodic distribution of the simulation at equilibrium according to the best policy done by the agents. Right? And that's very cool, and it makes these high dimensional problems, which used to be just sort of out of bounds, tractable. Hooray. Here's the algorithm. I'm probably going to run out of time on this talk, so I might not run through this. But check out the paper if you like this idea. It's a great paper. One thing that's interesting about it is for the objective function here, here's back to the original problem. You can plug in this lifetime reward function as the loss function and get most of the way there. It's quite interesting. What's happening more broadly is we're getting better algorithms, which means that more realistic and complex models are kind of within reach, and there's much, much cheaper compute. People are investing tons in cloud compute. You get free GPUs from some people trying to sell you a cloud computing environment. So you can approximate things to a much less rough degree, much finer grained approximations, discretizations of these spaces. And then that means that rather than needing to hard code all these models, which is not great for reproducibility, it's more and more possible to decouple model configuration from analysis algorithms libraries, kind of echoing what Dynair accomplished and still accomplishes, but with a wider range of models. And this is what we're aiming for as we're designing and building out HARK 1.0. And one thing we're trying to do is design not exactly domain-specific language, but a kind of markup language for models with a few principles in mind. So one is we want to be able to modularly compose parts of the system with reusable blocks, kind of like Lego. So you might have your consumer agents, you might be able to modify those consumer agents with other kinds of properties, and then plug those into various kinds of market constructs, maybe introduce a banking sector, et cetera, right? And we want these to be human and machine readable, so they're easy for people to read and write, even people that are not super trained in the particulars. At least we want practitioners to be using this stuff, not just the academic researchers who are building it, right, ourselves, right? And then there's portability. We want this to be agnostic to any particular platform because for any particular model, the state of the art for how to solve it might require certain approximations today and might be not as perfect as you might like. But it might be that in 2 years there's an advance in chip design or something, and you want to take the same model and benchmark it against the old technique and use the new computational technique to work with it. So what might this look like? This is all in PRs in the ARK library at the moment. It's going to be released at some point. So here's some YAML on the left, and it translates to these equations on the right. And so we've got the dynamic equations. We're specifying which of the variables are control variables. We've got bounds on those variables, so you can't can't consume more money than you have, M. We've got a reward function here, and we've got in the background a kind of library of probability distributions that can be used for the exogenous shocks. So things to notice is it's a flavor of YAML. We're using Sympy right now to sort of parse these expressions into symbolic expressions mathematically, and from there you can go to lambdas. They can actually be taken straight from Sympy to JAX now. And then if there's a variable that's out of scope, so here R is referred to but not defined in the dynamics, that scope can be provided by another block of YAML. This is a calibration dictionary, and we're just going to allow R, the rate of return, to be here. And the parser is going to know, okay, this block knows to pull that value from a broader scope that's provided by the context. But suppose you want to elaborate on this consumer's choice. So before we had consumer getting some income, getting rate of return, eating, and then there's tomorrow. What if now they get to, I see, yes. Yeah, what if now they're exposed to the stock market? They have a risky investment opportunity. So the risk-free asset that they could be spending, they keep cash under the mattress or they gamble with it. And so there's a log normal distribution here. Oh, 5 minutes, right. Thank you. Now R is being produced by the dynamics of this block, and it's being set endogenously, and we can let that definition of this variable trump the earlier calibration. And so then you could line up these blocks saying, okay, we want to start with the consumer block, then the portfolio block. We want to do a variable rename at the end, so the end of state variables and the beginning of state variables are end of period state and beginning of period state properly loop around. We give it a parameter, calibration dictionary, and we say, oh, it's a dynamic problem, so we have to provide a discount factor. And this is a simple example of how we might set this up, and then interpret this into a model. So there's a big roadmap we have in mind for more elaborate kinds of models. There's aggregation of different agents to a market. There's this birth, aging, and mortality issue. There's a question of what happens if you have agents with different kinds of roles, like consumers and firms and banks. This brings in a lot of game theoretic complexity. Maybe we'll talk about that some other time. And then alternative forms of discounting, time inconsistent preferences, hyperbolic discounting, endogenous discount factors. anyway, we're building all this as part of HARK 1.0 now, and we're also looking for help in thinking about how to design this language. So we're trying to figure out how to establish a working group where we can get inputs on something that would really be useful for people, not just our team, but also people more broadly. So open to ideas about that. Thank you very much. Please hit me up with any questions now or later.
Okay, please raise your hand for questions for the people in the audience, and there's also the Slack channel if you want to ask questions from online.
This is a great talk, and you brought up a lot of the things that are really hard about agent-based modeling and economic modeling. One thing that's kind of persistently vexing is having to compute big old integrals, numerically or otherwise, and this kind of discretization problem that you mentioned. It seems like everywhere I go lately, I hear people talking about neural operators. Is that something that you've thought about or considered building in to overcome just the kind of integration question?
I don't know what you mean by neural operator.
Just a neural network that's learning functional forms instead of data points.
I think yes. I mean, there's a lot of talk about just using JAX in a dynamic programming setting, and you know, to the extent that neural just means nonlinear regression, as we learned this morning.
I love that.
I think that's kind of what's up. Yep.
Yeah, cool.
Other questions?
Thanks. Great talk. I know you're not an economist, but if I understood it right, you know, in a lot of cases, what you're trying to look at is agents optimizing for long-term wealth. To what extent is there research that validates that that's how consumers actually behave versus, you know, some subset of consumers maybe, you know, likes to drive a BMW when they could drive a Hyundai and, you know, end up with more long-term wealth?
Okay. It's actually not the case that this research thinks that agents are always trying to optimize long-term wealth. There's a very interesting theory of buffer stock or precautionary saving, which says what under certain conditions of like impatience and sort of uncertainty about income, what agents will want to do is target a level of wealth that is the right balance between current consumption and sort of having a buffer in case of the future. And then when you put in aging and mortality, then what the theory says is people want to save for retirement as much as they can, but knowing that retirement will eventually end, right? So it's a little bit more complicated than this wealth optimization. That's according to the theory, right? And then in terms of validating that theory, there's techniques of structural estimation where you take data from, you know, tax records. There's data that's used to calibrate these models and estimate variables in them. The work I've seen that I'm most familiar with, you know, will do things like say, what is the distribution of discounting that explains the distribution of wealth that is there empirically? But there might be other variables that might explain that distribution of wealth, and you might say, well, there's all these other factors. There's sociological factors that are not being included here. There's this and that. I come from a computational sociology background. I'm excited about building those in, which is why I'm stoked about these deep learning methods and more expressive modeling languages. Does that answer your question?
Yeah, that's great. Thank you.
Other questions? Okay. Oh, yeah.
I sort of come from a background that's related to this, and I'm curious if you can elaborate just a little bit more on like how the machine learning takes us past the barrier of just the recursive dimensionality. Because like usually when you had something, you end up transforming things in such a way that you're just doing matrix multiplications, or more so inverting matrix multiplication. So how are we getting around that?
Okay, so recall here, step 2, the expensive step. It turns out there's techniques where you can basically take this optimization step almost to nothing. But the expensive step is looping over the state space. And at each point in that state space, doing the backup of the value function, saying, okay, given the current value function I'm expecting and the best possible move I can make today, what does that imply about the value function at the beginning of this period? Right. What if, rather than doing this whole grid over an n-dimensional state space with k points per dimension, so it's k to the n, that's huge, you just pick a number that's within reach, like 10,000 points, right? And then, rather than doing that backup over the grid, what you do is you say, given the current policy state of the model, I'm going to sample 10,000 points. Given the kind of exogenous noise that's available, what do I end up with in terms of state? What state does the system end up in? Then, what is the gradient of the loss function on those points, and back that up? Right. And the thing is, you're only picking those 10,000 points at each step rather than k to the n. But every time you do that step, your sample converges on the ergodic distribution of the system at this optimal policy. It turns out that works out. It contracts down.
Okay, if there's no other questions, let's thank our speaker again.